Solving general chemistry problems. Electrochemistry. The zinc-copper Daniell cell and its later variant, the gravity cell, were the original source of electrical power to telegraph systems in Britain and North America. It was also the first definition of the unit of volt. The Daniell cell's potential is about 1 volt. However, by modern definitions, the standard cell potential for the Daniell cell is about plus 1.10 volts. What happens if we double the size of the entire cell? What happens if we just double the size of, for instance, the copper electrode? What happens if we just double the volume of, for instance, the copper sulfate solution? What happens if we double the concentration of the copper sulfate solution? Cell potential is an intensive property of the system. Like temperature, it does not change with a change in size of the system. The doubled cell will have the same potential of plus 1.10 volts. It will, however, last for twice as long. The larger copper electrode? Again, no change in the cell potential. Lifetime would be the same too. However, a larger current would be drawn from the cell, ignoring for now limitations induced on the zinc side. The larger solution volume? Same cell potential. Any changes to cell lifetime would depend upon the zinc half cell. The greater concentration? Now we change the cell potential. The Nernst equation will describe how concentrations and pressures in the case of gases control a cell's potential. The question at hand is, how does the activity of reaction participants affect the reaction? We know that in general chemistry, we substitute species concentration or partial pressure for their activity. For dilute substances, a substitution would be acceptable. For a lot of situations in general chemistry, we probably should be more precise with activity, but we ignore it so we can focus instead on the chemical principles we are studying. In thermodynamics, we know that for reactions at constant temperature and pressure, which are conditions we expect to find most commonly in general chemistry, monitoring changes in the Gibbs function provides direct insight into the reaction direction and the conditions of equilibrium. Perhaps the most important thermodynamic equation is delta G equals delta G naught plus RT ln Q. The Nernst equation utilizes the relationship between delta G and a cell's potential E and makes the substitution of minus NFE for delta G. So we obtain minus NFE equals minus NFE naught plus RT ln Q. We can regroup that to obtain E cell equals E naught cell minus RT over NF ln Q. This is the Nernst equation. It is the same equation as the delta G equation, just recast to be more useful for redox reactions. R and F are the usual constants, the S constant and the Faraday constant. T is the temperature. In the absence of other information, we take it to be 298 Kelvin. N is the number of electrons transferred in the reaction being considered. Its value is unique to the way we have chosen to write the balanced reaction equation. Such a choice will also dictate the form of Q, the reaction quotient. With correct units, R in joules per Kelvin mole, T in Kelvin, F in coulombs per mole, and N in moles per mole, we see that RT over NF has the units of volts. With ln Q being unitless, it adds nicely with the cell potentials. The reaction quotient Q is the usual products over reactants raised with an exponent to the correct stoichiometric coefficient. As in thermodynamics, we replace the activity of all solids and pure liquids with just one. Because of that, they are usually left out of the expression altogether. And that is why doubling the size of the copper electrode does not change the cell potential. Gases appear as their partial pressure measured in bar, and solvated species appear as their concentration in molarity. Solvents are treated as pure liquids and so do not appear in the expression for Q. Recall that while we use the numbers for bar and molarity, the units do not appear in Q because they have been cancelled by the reference state condition. Just put in the numbers. In general chemistry, we so often solve problems with the temperature of 25 degrees Celsius or 298 Kelvin that it is helpful to calculate the RT over F constants for that temperature. The number has units of volts and equals 0.025,693 volts, often rounded to 25.69 millivolts or even 25.7 millivolts. So the Nernst equation now looks like this. Again, the variable n is the coefficient for the electrons in the balanced redox process. Another variant is found to be useful. If we convert the natural logarithm of q into the base 10 logarithm, a constant of ln 10, which is 2.30259, and just often rounded to 2.303, is multiplied into that constant. The equation now becomes this. The place the base 10 log comes in useful is when discussing a pH meter. It is a meter that measures the pH of a solution. It is an electrochemical cell, and the voltage produced is a direct measure of the hydrogen ion concentration, or in other words, the pH of the solution. Since pH is by definition a base 10 logarithm, it makes it straightforward to relate the measured cell potential to the solution's pH. And we'll see some examples of this. What is the potential of the Daniell cell under standard conditions? What is it if the zinc 2+ concentration is decreased to 0.1 molar? What if it's decreased to 0.01 molar? Well, this is the zinc-copper cell we've been seeing so often. The standard reduction potentials are given here. Copper is the most positive, so it will be the cathode. Zinc will be oxidized. The overall reaction is copper 2+ plus zinc goes to copper plus zinc 2+. The standard cell potential is, as always, cathode minus anode, or 0.340 minus a minus 0.763, or plus 1.103 volts. Look at the reaction equations. We see that, as written, 2 electrons are transferred from the zinc to the copper, n is equal to 2 for this reaction equation. The reaction quotient Q is formed by remembering products over reactants and leave out the solid phase material. Their activities are just 1, so Q is then zinc 2+ over copper 2+. The Nernst equation is this. Note that the solid phase electrodes do not appear in the expression. They really are there, but they are just the number 1, and are always the number 1, no matter how big or small they are. So even though during that reaction the copper electrode increases in size and the zinc electrode decreases, the contribution to the reaction quotient, and hence to the Gibbs energy, remains the same, and we can proceed without thinking further about them. So let's see what the Nernst equation predicts for variations in concentrations. First, what is the potential under standard conditions? Well, all solvated species are 1 molar, and we stick number 1 in for both of them. 1 divided by 1 is 1, and the logarithm of 1 is 0. The cell potential is precisely the standard electrode potential of 1.103 volts. Now, presumably that would have been obvious to you, but it is nice to know that this equation correctly predicts that value. What about when we decrease the zinc concentration to 0.1 molar? Well, copper is still 1 molar. Substitute for zinc, solve to find the cell potential to be 1.133 volts. The cell potential has increased by 30 millivolts. Mathematically, you can see this because the argument of the logarithm is less than 1. So the log is a negative number, making the second term overall positive, which will increase the potential. Chemically, you should expect this too. Think of Le Chatelier's principle. The zinc ion is on the product side of the reaction. We decrease its concentration so the reaction will respond by trying to counter that change and produce more zinc ion. That is in the forward direction, so we would expect an increased potential in the forward direction, or a more positive cell potential. And decrease the zinc concentration to 0.01 molar. Substitute and solve to find the cell potential, 1.162 volts. Another 30 millivolts increase. It's not quite 30, it's really 29.6, each factor of 10 change, but rounding off gives this result. Could you now predict, without doing the Nernst equation calculation, what the potential would be if we were to decrease the zinc concentration another factor of 10? Would you predict it to be about 30 millivolts higher again? It would be about 1.192 volts. What will happen if we decrease the copper concentration instead, while keeping the zinc at 1 molar? Well, copper is on the reactant side. If we decrease its concentration, Le Chatelier would tell us that the reaction will tend to go more in reverse to compensate. We might expect this potential to decrease in this case. Copper concentration is 0.1 molar. Substitute into Nernst. This time the change is in the denominator of the reaction quotient. 1 over 0.1 is equal to 10. The log of a number greater than 1 will be positive, so the second term will be overall negative and lead to a decrease in cell potential. You are perhaps not surprised to find it is about 30 millivolts lower at 1.073 volts. And down to 0.01 molar. Substitute and solve. Again, about a 30 millivolt drop down to 1.044 molar voltage. So think about this situation. What will be the cell potential if we decrease both copper and zinc by the same amount, say to 0.1 molar? Look at the Nernst equation. Envision these two substitutions. What is the log term going to do? Or conversely, think of Le Chatelier's principle. We decrease the reactant concentration and at the same time the product concentration by the same amount. What will happen? Well, hopefully either your mathematical sense or your chemical sense or both guided you to suggest that the cell potential will be the same as for that under standard conditions. Q will again have the value of 1 and the log term will be 0. Even though the potential is plus 1.103 volts, the same as found under standard condition, the cell is not at standard conditions. It just has a potential that happens to be the same as that found under standard conditions. Here is another cell. See if you can observe any similar or different trends. We will look at a cell formed from aluminum and indium. The associated oxidized ions both have a valence of plus 3. Here are the relevant standard reduction potentials. Indium is the most positive, or at least negative in this case, so it will behave as the cathode and aluminum is going to be oxidized in the cell. The overall reaction is indium 3 plus aluminum goes to indium plus aluminum 3 plus. The standard cell potential, cathode minus anode, is plus 1.324 volts. There are 3 electrons transferred in this reaction, so N is equal to 3. The reaction quotient, products over reactants, is aluminum 3 plus concentration over the indium ion concentration. We put all this together and write out the Nernst equation for this reaction. So how will decreases in the aluminum 3 plus concentration, which is on the product side, manifest itself in changes in the cell potential? Recall that in the case of the zinc copper Daniell cell, the potential increased by about 30 millivolts. Consider the aluminum concentration to be 0.1 molar. You might again predict, based on your chemical insight from Le Chatelier, or your mathematical insight, knowing how logarithms work, that the cell potential will increase. The value comes out to 1.344 volts. It is an increase, but this time the increase is only about 20 millivolts rather than the 30 millivolts as found for the Daniell cell. The difference? The change in Gibbs energy is spread over 3 electrons being transferred rather than 2. Change aluminum to 0.01 molar. As you might have predicted, the potential will increase by about another 20 millivolts, closer to 19.7 millivolts. I think you can see how changes in indium concentration would affect the results, so I'm not going to go through those calculations. Here's another example. Consider the following cell involving oxygen gas, water, and 2 oxidation states of the element thallium. Consider a decrease by a factor of 10 of each of the participating reagents, thallium 3 plus, thallium plus, H+, and O2. Here are the standard reduction potentials. Thallium is most positive, so it will be the cathode. None of the reactants are solid conductors, so some inert electrodes must be introduced to transport electrons and connect to the external circuit, and we've used platinum for this example. The balanced overall reaction must be this. Now, we have to multiply the thallium reaction by 2 to balance the electrons. Hence, N is equal to 4 for the reaction as written. The standard cell potential is plus 0.023 volts, or 23 millivolts. Because the 2 half reactions potentials are so close to each other, the cell potential is rather small. We can write down the reaction quotient Q. The water is a solvent and will be given the activity of 1 and will not be explicitly given in Q. The oxygen gas appears as its partial pressure in bar. Again, the reaction quotient is unitless because each term separately is in fact divided out by a reference state and the units have already been cancelled out. Just put in the numbers. We use placeholders for each variable that seems to imply pressure or concentration, but they are just there to remind us what goes in. There are 4 terms that have to be considered in determining a cell potential: thallium 3 plus, 1 plus, hydrogen 1 plus, and O2 gas, and we will look at each of them in turn. So here is the Nernst equation that will let us determine that value. We will consider a 10-fold decrease for each of these terms in sequence. First, thallium 1 plus. For this calculation, we are assuming that the other components remain at 1 molar, and their mathematical contribution to Q is just 1. Only the species that changes, in this case thallium plus, needs to be considered. It is, however, important to not forget the exponents involved. Here the thallium is squared. The Nernst equation becomes this, and we see that the potential has increased by 30 millivolts. Now, this is as expected from our chemical ideas of Le Chatelier's principle. We decreased a product species and the reaction will increase its tendency to go forward to compensate, resulting in this case with an increased potential. What about the H+? Write out the Nernst equation again. The difference, however, is the H+ appears to the fourth power in Q. This makes for a different result. We substitute and find the cell potential now is 0.082 volts, an increase of 60 millivolts. As a product species, it makes sense that its decrease would lead to an increased potential. What about the oxygen? We substitute for the partial pressure of the oxygen gas. Our reference state for gases is now 1 bar, so we must use pressure units of bar. Since the question provides them in that manner, we can just proceed. But if we were given in other pressure units, torr for instance, we would need to make a change before proceeding. We substitute and find that the cell potential will now be 0.038 volts or 38 millivolts, an increase of 15 millivolts. So the stoichiometric coefficient makes a big difference. If the species appeared with a coefficient of 1, 2, or 4, an order of magnitude decrease in its concentration or pressure had an impact through the Nernst equation to increase the potential by respectively 15, 30, or 60 millivolts. What about the thallium 3+? Well, you might expect it to decrease the cell potential. Substitute, calculate, and the cell potential is a negative 7 millivolts. What does the negative sign mean? It means that the reaction direction has changed. Now the oxygen half cell is experiencing reduction. It is now the cathode. The thallium half cell is now the anode. The reaction is proceeding now in the reverse direction. Is there any chemical insight we can glean from this? A 1 molar thallium 3+. For that, the reaction was proceeding forward. At 0.1 molar, it was going in reverse. Somewhere between these two conditions, the reaction must have been at equilibrium, with the forward reaction equaling the reverse reaction. What would that concentration be, do you think? The cell potential was first a positive 23 millivolts, and then at 0.1 molar thallium 3+, it was a negative 7 millivolts. What is the equilibrium condition? Well, it happens that when a cell potential, not the standard cell potential, so don't mix up the two, equals 0, is when it reaches equilibrium. We can back calculate to find the concentration, which produces E equals 0 and is the equilibrium condition. So 3.5812 equals the ln of the reciprocal of the square of the thallium 3+ concentration. Exponentiate both sides. 35.915 is the reciprocal of the square of the thallium 3+ concentration. Take the square root of the reciprocal to find that the concentration of thallium 3+ at equilibrium, given that all the other reaction components are at standard conditions, is 0.167 molar. This is between 1 molar and 0.1 molar as we expected. Hopefully you can see how much information can be obtained from the Nernst equation.